First speaker for this session is Pascal Lee, and there he is. Hi, Pascal, who's going to be talking about Phobos and Deimos, science and exploration objectives for humans. And Pascal, you'll have about 13 minutes. I'll give you a 2-minute warning.
Sounds good. Thank you. Good afternoon. Thank you for staying. So I'm going to present to you a sort of a perspective that's narrowly focused on a few specific issues that I think are important to consider in this bigger picture of the idea of getting humans to go to Mars orbit and visit the moons of Mars. And I have control. So first of all, just one slide to say even why are we talking about humans going to Phobos and Deimos. The idea is not new. It dates back to the early thinking of humans going to Mars. One of the first studies that was really published about sending humans to Phobos and Deimos specifically was by Fred Singer, and then shortly after there was another one by Brian O'Leary. The NASA 90-day study also included a Phobos-Deimos option. But the idea is that going to Mars orbit is going to cost a lot less than going to the surface of Mars. And of course, it doesn't do the same thing. So why would you even consider doing something just because it's less costly? Well, there are some classical arguments for going to Phobos and Deimos. It doesn't take much delta V to get there from Earth, 5.5 to 7.5 kilometers per second, depending on whether or not you're going to use Mars aerobraking, versus 8+ kilometers per second to land on the moon. And so it's actually, in terms of delta V, cheaper to land a pound or a kilogram of payload onto the surface of Deimos or Phobos than it is to land it on the surface of the moon. Okay? In spite of how far Mars is, the gravity on Phobos and Deimos is so weak that you actually don't expand a lot of delta V to land there. Now, of course, it's very different for people. People, you have to feed them all the way out to Mars, and that, of course, increases the mass you have to carry. But otherwise, in terms of cargo, it's cheaper. Now, it was also argued that Phobos and Deimos are essentially natural space stations. They offer stable orbital platforms for Mars observation and comms. An argument that's often presented, even still today, is that they allow you to do low time latency robotic teleoperations on Mars. To me, that is actually an argument that's a little bit oversold, because the time delay in radio signals between the Earth and Mars is actually not the real bottleneck that's delaying or making Mars rover exploration slow. It's the time it takes for the science teams to analyze the data, make decisions on what to do next, upload commands. That is the real bottleneck of teleoperating rovers on Mars these days. The Department of Defense, DARPA, have rovers that can zip across the landscape at 50 miles per hour in all-terrain vehicles. So if it was a matter of just covering distance, we have the robotics capabilities to handle this now. We could go much faster on Mars. So the notion that somehow we would get rid of the time delay in radio signals to really speed up robotic rover exploration, for example, is not really a strong one. On the other hand, there are some systems, like flying a drone, that are requiring real-time interaction with a human observer or scientist behind the drone that could really gain from being in Mars orbit, of course, versus being on the Earth. It's been argued that you could do good science for Mars's moons and small bodies in general. Also, these moons might offer resources, H2O in particular. Now, none of this actually made the dial move, really, from the standpoint of NASA doing serious studies, until a number of additional arguments were presented. In the past decade or two, we've been now aware that we have Martian meteorites, and that the regolith of Phobos in particular might essentially be a library of Alexandria of Martian materials collected throughout Phobos' history around Mars, from all over the place on Mars, and nicely quarantined in the regolith of Phobos. Not large amounts, but nevertheless something that could be really interesting. They could also serve as glove boxes for Mars and other places where you would quarantine material that is brought up from Mars. They might be a good place to cache samples that would be collected robotically on Mars for humans to retrieve, and that's an idea I want to revisit a little later. the big argument really is that you can reach Phobos and Deimos as opposed to the surface of Mars much sooner and for a lot less cost. And so in terms of having a Mars exploration program with humans that needs phasing with some worthy milestones along the way, going to Mars orbit and visiting the moons of Mars along the way is not a bad idea. And of course, the idea is that if you're actually going to Mars orbit, well, that will really catalyze, serve as a catalyst for getting humans to Mars itself. So that plus the fact that they are inherently exciting to explore. So a quick sense of scale. This is Itokawa next to the space station, which is about 100 meters across, the space station. Itokawa and ISS are now at the very upper left, compared to Phobos and Deimos at the same scale. So Phobos is 27 kilometers long, Deimos about 15. Morphologically, they're very different. Phobos is much more rugged, it seems, than the surface of Deimos. Deimos is believed to be heavily fractured in its interior, might be a rubble pile almost, with a thick regolith dusting at the surface. Its density is lower than that of Phobos. Phobos has grooves, might have internal strength, coherence throughout. Anyway, two objects that physically are quite different, actually, although both are relatively large. Now, a few things to bear in mind. The gravity, of course, is very low on these small bodies. If you are an astronaut wearing a spacesuit, you plus the spacesuit might weigh up to 650 pounds. On Phobos, you would have a felt weight of 0.3 pounds. Okay. So if you push yourself off the surface of the moon, I don't need to tell this to Jack, but those of us who have not been to the moon, if you jump at 2 meters per second as a takeoff velocity, you will rise to about 1.2 meters on the moon. On Phobos, you will rise to 350 plus meters. That's higher than the Eiffel Tower. Okay. And the total time of flight is at the lower right here, would be 11.7 minutes. Okay. Anyway, these are dynamical realities to consider, and it's going to be, of course, very hard to extrapolate our experience on the Earth or the Moon to a place like Phobos and Deimos. They have very low albedos as well. These typical, beautiful, color-rendered images that are, of course, enhanced that we often see are not really depicting the real albedo or reflectivity of these bodies. They have albedos of order 6 to 7%, which is similar to asphalt. You are essentially visiting 2 lumps of coal when you are exploring Phobos and Deimos. Okay. Now, in terms of the science, there are lots of things we could address, but there are some big mysteries. I'm going to focus quickly on a summary of the issue of the origin, their nature, and then the issue of water. So the origin of Phobos and Deimos is still a mystery, where they form by co-accretion with Mars. In other words, made of the same material, essentially, and possibly even being leftovers from Mars' own formation. Were they captured, in which case they would be foreign objects. And because of their spectrum, it's a D-type spectrum. It's found mostly in the outer main belt or beyond in our solar system. They might be bodies that are from the outer main belt or beyond, so captured from far away. And then the third hypothesis is that they might be reaccreted Mars giant impact ejecta. Okay? We should bear in mind that Phobos and Deimos might have different origins, and there's also the issue of a net transfer of Deimos regolith to Phobos going on as we speak. So this is Phobos with a grid sort of network just to orient you. There's a sub-Mars point, which is, of course, the satellites are synchronously locked. The sub-Mars point is shown here, and the crater Stickney is on the leading side of Phobos as it goes around Mars in the quarter that's towards Mars. Now, this is a nice map that was created by Mihaly Horanyi when we were working on a proposal for a mission to Phobos, a discovery mission proposal to Phobos, which was not selected. But this map shows nicely the accumulation of ejecta and dust that is essentially shed by Deimos onto Phobos. And where it's red, you have maximum deposition. Where it's gray, you have minimal deposition. The maximum deposition is of order 1 meter per 10 million years. Okay, so that's 10 meters in 100 million years, 100 meters in 1 billion years. So the trailing side towards the south of Phobos might actually have a large amount of grit and regolith dust that has been drifting in from Deimos over time. Okay. Incidentally, this also might tell you that the physical properties of the regolith on Phobos might be very ununiform. The regolith could be very unconsolidated, uncompacted, fluffy near the maximum deposition sites, whereas where it's minimal, it might be different physically. Additional evidence that there might be material that's drifting in from Deimos are the fact that we find these red-streaked craters on Phobos, and they have been interpreted by Heather Smith and al. As possibly being the signatures of low-velocity impacts of Deimos material onto Phobos. So this would be dark reddish D-type, truly D-type Deimos material crashing onto Phobos. So a lot of the D-type spectrum that is presented by Phobos might actually not be truly characteristic of the nature of Phobos. And in fact, this particular area that we see at the rim, on the rim of Stickney, might actually be the true Phobos. It's slightly bluer. It's still red spectrally, but in the near-infrared and visible, but it's termed the bluer unit of Phobos. And the bluer unit might be the true Phobos, and it's only seen in about 10%, 10 to 15% of the surface of Phobos. Now, in terms of the water content that Phobos and Deimos might offer, this is a table arguing how much water they might have contained originally when they formed in the three origin hypotheses, the three main origin hypotheses that are considered. To make a long story short, the classical view had relatively small amounts of water, including the Mars impact ejecta scenario that would have predicted that there would be none. Until recent developments, there have been a number of papers published on how richer the inner solar system might have been in water-rich planetesimals and asteroids, the discovery of water-rich S-type comets coming in from the outer solar system that were once in the inner solar system. That's Meach et al. 2016. Papers that are describing how the moon actually is not devoid of volatiles and has water itself by Sal et al., Hui et al. And a paper we wrote with Truong, who's a student of mine, recently about how even on Earth, the tektites, the Australasian tektites that have been superheated, went suborbital and have fallen in some cases back down in Australia after a suborbital hop and were heated to high temperatures, are still not devoid of water. And so water is expected to be present in the original materials forming Phobos and Deimos in all three scenarios. Okay. Yep. So this is an argument that there's even a hypothesis that Phobos and Deimos might be genetically connected to an object like Don Quixote, which is also a D-type that has turned out to be a comet. So in these scenarios, Phobos and Deimos could be really rich in water. We've been trying to model the interior survival of water over time in the different impact hypotheses or origin hypotheses. And so, of course, the variables are not well constrained yet because we still don't have a good handle on the internal structure and whether it's homogeneous or not Phobos and Deimos today. The upcoming robotic missions, JAXA's MMX, NASA's Mars Comms Orbiter, ESA's Phobos Sample Return Mission, which hasn't been confirmed yet, are likely to resolve the origin of Phobos and Deimos and seriously constrain their internal structure. But we should also maximize these missions as opportunities as human precursors. So what would humans do? These are specific objectives or tasks that I think humans could be doing in the sense that they would be uniquely enabled. These are science activities or tasks that would be uniquely enabled by humans. Sample large ejecta blocks, which are hard to access up close by robotic systems. Look for exogenic materials from Deimos, Mars, the asteroid belt. Map the internal structure of Phobos at high resolution with seismic tomography, which requires very careful coupling of seismometers with the regolith. And also deep subsurface sampling, in other words, drilling to collect samples, perhaps beyond the red layer, the redder material layer, into the true Phobos materials where there's red material accumulated. Large ejecta blocks, we have evidence that there are several. This is the space station to scale. Exogenic materials, this is just a token image of the surface showing a pile of rubble that crashed there. The grooves in the interior might still be active if the grooves have anything to do with internal structure and fracturing. This is actually one of the few landslides ever reported on the walls of a groove on Phobos. And then beyond the science objectives, there are exploration objectives, such as retrieving cached Mars samples, which I think would be really exciting. If we could spend the upcoming decade collecting with robotic missions samples from different locations at the surface of Mars, but instead of bringing them back to the Earth where there are planetary protection concerns, we just cache them on Phobos in Mars orbit. And then have these samples be high-graded and retrieved by the first human crew that goes to Mars orbit. That would enrich the scientific return of a human mission to Mars orbit dramatically. I'll skip along by showing that we've been looking at how some of these objectives come up with mission requirements that require either a fixed infrastructure on site or mobility systems that allow you to roam the entire body. There's an ongoing study or effort to, and it's a big team effort, led by Mike Gernhardt, to really understand in more detail how we might go about conducting a human exploration mission at Phobos and Deimos and what types of science we might do. Paula Bell, among others, has led a study of what types of activities we might do at different locations, and he does admit himself that not a lot of thought has gone yet into sort of the types of tasks you would do per region, but in general, there's a series of sampling tasks and subsurface sampling as well. So I'll just end by saying that to me, the idea of having humans go to Phobos and Deimos is really something very exciting. It presents us with some challenges that are new. The whole effort led by Mike Gernhardt has the stipulation that we're not creating any major systems that would not be needed for Mars Forward. And so the idea is to really do this opportunistically as opposed to having an entire sidetrack to go to Phobos and Deimos. We could use MMUs or resuscitate them. And where there are concerns that you might essentially fly off and not come back, there are discussions of doing tethered jetpack explorations of Phobos. Okay. So this is my final map, where we begin to map places where you might find thicker regolith and places that are more hard to couple a seismometer, for example, with the regolith or the interior, and places where it might be thinner, places where Mars is visible or not, places where you might have distinct low-velocity impact structures, places where the Blua unit is better expressed. And so over time, I hope to see this map mature with the input of the entire community. We're also talking about possibly holding a 4th international conference on the exploration of Phobos and Deimos at Ames next summer, but it's not confirmed. It's just a thought. If you have any feedback on that, they're welcome. All right, thank you.
Thanks, Pascal. For the panel, yeah. So we'll take questions like with the other sessions at the panel at the end of this session. So.